Hello, guys. Akhenaten here. So today we are going to be looking at a very elegant and simple visual proof of the famous Pythagoras theorem, and this proof is simple, visual, intuitive, and it uses the charming concept of similarity, specifically the similarity of triangles. And apparently, it was Albert Einstein's favorite proof as a student. I hope that I will be able to communicate just why Einstein might have liked this proof by the end of this presentation. All right, so what we need first is a simple property of right triangles. So we have, let us say that we have two similar right triangles. So we have two triangles PQR and LMN, which are both right angled. And well, we can mark one of these as the right angle. And of course, the corresponding sides are PQ and LM, PR and LN, and QR and MN. So that should be clear from the way the lengths are named, A and A dash, B and B dash, C and C dash. We are told that these two right triangles are similar, so we can use the result that the sides will be proportional. So what we get is A dash by A is equal to B dash by B is equal to C dash by C. So what this gives us is that A by C is equal to A dash by C dash. So let us call this K1, right? And B by C is equal to B dash by C dash. So let us call this K2. So now let's calculate the areas of PQR and LMN. Of course, we know that the area of a right triangle is half the product of the two shorter sides. So the area of PQR, so we are going to write the area of area just by I'm going to designate area just by putting a bracket. So area of PQR is equal to half AB and that will be equal to half of K1C, half of K1C into K2C, right? So so one moment. Half of K1C into K2C is equal to half K1 K2 into C square. At the same time, what can we say about the area of LMN is equal to half of A dash B dash is equal to half of K1 C dash into K2 C dash, and one moment. And that is of course equal to half of K1 K2 into C dash squared. So combining those two equations, so what we get is that area of PQR by area of LMN is equal to C square by C dash square, right? Or we can write this in another way as area of PQR by C square is equal to area of LMN by C dash square, right? So you look at this, these two right triangles, PQR and LMN. So their areas are proportional to the squares of the lengths of the hypotenuse. So that is a result that we are going to exploit in the proof proper, which will follow. Okay. All right, so now we get into the proof proper. So we have the right triangle ABC. AB is equal to A, BC is equal to C, and AC is equal to B. So we marked this all on the triangle, and of course we have made a construction, that is we have drawn AD perpendicular to BC, and angles. Of course, BAC is 90 degrees. So the we're dealing with a right triangle ABC, and BAC is equal to 90 degrees. That's also equal to ADB and ADC. So these are 90 degrees. ABC is alpha and ACB is designated as beta. So all right, so this is the setup that we have. Just absorb all of this. So now what we're going to do is, one moment. All right, so now observe the triangles ADB and ADC. One thing that's reasonably clear is that the areas of these two triangles ADB and ADC add up to the area of ABC, right? So we'll write that down as ABD. So we'll just write the bracket for area. So ADB plus ADC is equal to ABC, right? This is something that's visually immediately apparent. So now we're going to try to prove that all of these triangles are in fact similar to one another. So ABD is similar to ADC, which is similar to ABC. So if we can establish that, then of course their areas will be proportional to the square of the hypotenuse. And of course, as you can see, for ABD the hypotenuse is A, for ADC the hypotenuse is B, and for ABC of course the hypotenuse is C. So that will enable us to complete the result. As far as the similarity is concerned, it's actually pretty straightforward. So consider the triangle ADB and compare it with ABC. So now of course as far as similarity is concerned, only two angles, if you can show the two angles of a triangle are the same, then of course the third angle must also be the same, because the three angles of a triangle add up to 180 degrees. But in a right triangle specifically, obviously if you have two right triangles, one of the angles is already a right angle, so if one of the other angles is equal, then the triangles will be similar. And in this case the triangles ABC and ABD share the angle alpha, so which is of course one of the angles other than 90 degrees. So that means that ABC and ABD are similar, and exactly in that way, because they share the angle beta, ACD and ACB are also similar. And of course that means that ABD and ADC are also similar, because two triangles which are similar to the same triangle must also be similar to one another. So once we have that, we can use the result that we obtained previously. So we get that area of ABD by A square, because that's the hypotenuse of this triangle ABD, plus area of ADC divided by B square, sorry, not plus, which is equal to area of ABC divided by C square. So all of these will be equal, and let us say that this is a value m, right? So now what happens, the area of ABD will be equal to MA square, the area of ADC will be MB square, and since the sum of these two areas will be the area of ABC, we get MA square plus MB square is equal to MC square. And of course cancelling out m gives us that A square plus B square is equal to C square. The square of the hypotenuse is equal to sum of the squares of the other two sides, and we get Pythagoras theorem. So I hope you enjoyed this presentation. Thank you.